All right, so for number one, says the figure below shows a uniform beam subject to a linear increasing distributed load. And this is the formula for the beam deflection. So they give us E, they give us L, and they give us W0. And they're telling us to plot the deflection curve from x equals 0 to x equals 3 for the different values of I here. So pretty much what we're doing is we're plotting three formulas for each of the values of I. So three formulas with variable x. They give us all these numbers, so we could just assume, or not assume, we could just take this whole thing as a single constant or a single coefficient here. So we start off with the data set. Obviously, we start off with E, we start off with L, and W0. So we have all these values here written down. And then we start plotting the points here, not plotting points. We get our data table here. So for beam one and an I value of 0.00075 and then 0.0003 and 0.001 for beam three. So they want it to go from 0 to x value of 0 to x value of 3. And I think the professor said she wanted at least 10 points. So I think we have 12 or 13 here. So for this formula right here, we're pretty much plugging all these values in, into the formula here. So what we did, I'm gonna rewrite it here. So we set this equal to W0 divided by, and then make sure to put the bottom part in parentheses. So 120 times E times I, which would be this value right here, times L, then close the parentheses. So the reason I told you to put parentheses was because if you don't put the parentheses, what it's gonna do is it's gonna take a W0 divided by 20 and then multiply E, I, and L. So make sure that the whole denominator here is in parentheses. And then put this whole thing in parentheses if you want. I mean, it doesn't really matter, but just in case. Then you multiply that by this section right here. So it would be negative x. So x is right here. I think it's B11. Okay, so let's put this whole thing in parentheses. So it'd be negative x to the 5th plus 2 times L. L is right here. Squared times x, which is B11 again, cubed, minus L to the 4th times x, which is B11. Oh, B11. So here we have to log some values. So we have to log the values for E, L, and W0. So E is the C3 here. So lock all the C3s. Oops. Lock all the C3s. So this is C3, lock C9, not C9. C9 would be I, and then you have to lock L, sorry. Lock L, you have to lock W0, which is F3 here. B11, you can move that. You should be able to move X down, but not to the side. So what we're gonna do is just gonna drag this formula to the side and then down as well. So if we wanna be able to do that, then we have to lock the column. So you can move the X down for all the other X values, but not over. So we lock just the B here. And just look up here. So we lock just B here. So we can move it down, but not to the side. Then C4, we want to lock L here. And again, here B11, same thing, lock just the B. Then lock C4 as well, because that's your L. And then again, here B11, we lock just that. And then that's it. Click enter, and then you should get 0 here. And if I drag down, I should get the same values. Oops, what's going on here? Oh, I didn't lock C10 here. All right, so you're supposed to lock this. So you're supposed to lock the row here, because for I at least, we can't move it down. So it has to stay at this row 9. So we lock. Wait, why is it a C10? All right, so it's not supposed to be C10. This is supposed to be C9. And then you lock the 9 here. Then you click enter, and you should get those same values. So we see we have 1.4. So 1.4, 2, 2.4. So if you could pretty much just take this, take it across, because of how we wrote this formula, we could just take it across and then drag it down. Whoops. Oh, it's because we didn't fix it on this one. That's why. Sorry. All right, so we copied the one that was not fixed. So there. Now it should be. Now we can copy it across. You see, now we get actual numbers now. Okay. All right, there. So now we have this graph. So it says plot the curves. So the first step is to plot the curve. So we can just delete this for now. So what we're trying to do here is plot 3 different curves onto a single graph. So you first start off with plotting one set of data. Insert, scatter plot, or this line graph. Scatter with smooth lines. Correct. So you would obviously add the axis titles and the legend, because you're going to be adding multiple lines here. So you obviously change this one to distance in meters. That'd be your value x. And then this as deflection. And here you just go to select data. So what you do to add another set of points here, you go to select data, and you would add a series, because each of these data sets is called a series. So you would add. So now you're trying to add beam 2. So you just name it beam 2 or whatever you want to name it. You're going to choose your x values, same x values as the other data set. But then make sure you delete this one, and then highlight the y values for beam 2. And then you should have another one here. And then you just repeat the same steps for beam 3. Beam 3, highlight the x values, highlight the y values for beam 3, and then click OK. And then now you should have 3 graphs here. So obviously you fix it up a little bit, and it should eventually look something like this. So deflection, distance in meters, and just beam deflection. And where's my legend? All right, there. include a legend there. You can move it down if you want, bottom there. So for the next part, you could do it how I did it. I use calculus, but if you don't know how to do that, don't worry, because it says you could just do it by inspection. It says by inspection or using the graphs, estimate the approximate value of x, where the maximum deflection point occurs. And it says you could also use your calculus knowledge, which is what I did. But you could just literally just look at the graph, and if you divided the x-axis into smaller points, and you could probably see that it's going to be at 1.34 or somewhere around that. And then now pretty much you just take the same formula that we did here, but instead of you see how instead of evaluating at one of these points, we're going to evaluate it at 1.34. So this is going to be our x value right here. So at this x, where the maximum point of deflection occurs, the maximum deflection is 2.6 to the 7. 2.6 times 10 to the negative 7. So you just take, and hint, they're all at the same, the maximum deflection occurs all at the same x, 1.34. And you just evaluate for each of the I-beams, for each of the moments of inertia at 1.34. And that's pretty much number one. So number two, you have body surface area. So you were given a height of 180 centimeters, and here is the sample they gave you. So first they tell you to plot the data on a scatter plot. So what you're going to do is just going to highlight it. All right, go to insert, scatter plot. You could choose whichever one you want. Here. So obviously you would fix this axis because it's starting at 0. But you don't want it to start at 0, so go to here, axis options, minimum, put it at 69, and that's the value here. And if we move this graph over, you can put the maximum probably at like 90. Or like 91, just to have it all inside the graph. All right, so now you would do the same exact steps we did up here to add another data set. So that you have to add it later, but so for part B, it says calculate the body surface area for the weight of the American individuals listed above using the Du Bois formula, which is commonly used to predict body surface area. So you're giving the same weights. I mean, honestly, you could just join these, put this right here, and not have to rewrite this, but I did this. So for same weights, so 84, 87, 90, you would use the formula here. So for the body surface area, you're giving 0.007184 times, let me just rewrite it. So this is equal to 0.007184 times the weight. So the weight is this one, to the 0.425 times the height. So this is the height to the 0.725. And you should get that. So you should get this, and then you could just drag it across. Except you have to first lock the height here. So make sure you lock the height. So it'd be C43, you lock both the column in the row, and then you just drag across. I should get the same numbers. Yeah. So Now to so it says compare graphically the data given with the area values calculated using the Dubois equation. So now you just get to compare graphically, you always have to put them in the same graph. So you go here, you go to select data, right? So you're gonna keep the same max values here, but you're gonna add another series. See here, you can see I added Dubois. You're gonna add, name it Dubois, and then go to X values. Obviously, same X values here. You delete this one, and then add the Y values. Click OK. You see now it's in gray. So I add another one, and it's called Dubois, and it's on top of the other one that I made. So, but this one's in gray. So you click OK, and then you should have your 2 lines. I'm just going to delete that. So that should be number 2. Number 3 is a little more involved, but so first you have to copy all this down, and then part A says determine the mean, median, and mode. So mean, you just do, you could just do average of all this data, 8.9, right? So you could also do, for median, you just use the median function, median, and you highlight the entire data set. For mode, you could do mode, and I'm not really sure if there's a difference between mode. Let's see, values. Let's see, returns a vertical array. So I guess if you want to find multiple modes, then you use mode multi, and then, but for now, we're just going to use mode single, and then you're just going to highlight the data set, and it's going to give you the mode. For standard deviation, same thing, standard deviation, S, because we have a sample here, and just highlight the data set, and it should give you standard deviation. So that's part A. Part B, it says create a pie graph to show the relative frequency distribution of the defects data using bins of length equal to 3, which interval shows the highest frequency. So if you want a pie graph, you need to have the relative frequencies. So the frequencies of the different bins. So here, we could just look at this, look for the lowest value, which would be 0, and then the highest value would be 17. So we know that we need bins equal to 3 that go from 0, that covers 0 and 17. So we'll go 0, 3, 3, 6, 6, 9, 9, 12, 12, 15, and 15 and 18. So now we're covering this whole data set. So then you put in your the upper limit, which is what you're going to need for this frequency function here. So the upper limit of 0 to 3 is 3, and 6, 9, 12, and so on. So for frequency here, so you notice this is an array. So I'm just going to delete this. It's going to change all this because it all depends on this. But so you're going to highlight this whole thing. You're going to press equal to, use the frequency function. You're going to highlight the data array. So this is the data, comma, and then the upper values. So now based on the upper limit, it's going to determine the frequency of each bin. So it's going to go what's between 0 and 3, and then what's between 0 and 6, and then subtract that from what's between 0 and 3, and then it's going to give you what's between 3 and 6, and so on. So now since it's going to give you an array, the frequency gives you an array, you could go Control Shift Enter, and now it gives you the frequencies for each bin. So now the relative frequency, you obviously it's it gives you a percentage, or so you go and click the frequency. So you set it equal to the frequency, and then you divide by the total number of values. So if it occurs in 2 data points out of 20, the frequency is 10%. So it's going to usually give you a number like a general, just like 0.1, and then you just go here and then change it to a percentage, and then just reduce decimal places because it's just all zeros. So for the count here, you would just use count. So you just count and it give you return 20. So pretty much just the frequency of that bin divided by the total number gives you a percentage, which is the relative frequency. And now cumulative distribution, pretty much, let's see. Okay, so part B, it says create a pie graph. So, okay, so now you have to plot this relative frequency. So you just go here, go to insert, pie graph, and then, so it's, you see how I have it here where each of the labels is set up to be the bins. And here it's 1, 2, 3, 4, 5. So you go again to select data. This is where you just change the labels. This is where you change the X and Y axis, the labels. So you see this is the horizontal, or just the categories. So in a pie graph, they're called categories, and in like a bar graph or line graph, they're called it's just the horizontal axis labels. So you go to edit, and then now instead of being 1, 2, 3, 4, 5, you want it to be 0, 3, 3, 6, 6, 9, 9, 12, and so on. You press OK, and you see now it's changed. So you click OK, and here you could add the legend. Right, hold on. This is, I'm sorry, this is the legend. You go to data labels, and then it gives you the percentages, right? And you change the chart title, and then that's how you get your pie graph. And then part C, it says what is more likely to happen in this factory to obtain 3 defects per 100 units or 10 defects. So let's see. Oh, okay, so for part B, it says which interval shows the highest frequency. So again, you see the relative frequencies. So 35% is the highest out of all these bins. So 6 to 9 shows the highest frequency. And that's for part B. Now for part C, sorry, it says which is more likely to happen, 3 or 10 defects. So we see 3. 3 could be either, honestly, since they actually no. So what Excel does for the frequency is it checks up to 3, and then here it checks up to 6, and it subtracts what's up to 6 minus what's up to 3, and then gets 3 to 6. So technically it's calculating what greater than 3 to 6. So it's not counting 3 in this value right here. So the probability of getting 3 is about 10% according to these bins. But if you go to 10 or 9 to 12, you see that's 30%. So probability of getting 10 defects is a lot higher than getting 3 defects. And you could also just look at the data here. If we count how many 3s there are, there is 0 3s. And if you count how many 10s there are, there's 1 10, 2 10s, and then 3 10s. So which is more likely? 10 defects per 100 units. So for part D, it says create the histogram and cumulative probability distribution function for this data. So The cumulative probability is, let's see. I mean, if we go, I think it was classwork 3. So you see, cumulative probability is pretty much just taking, just including all the way up to that bin. So the probability of getting anything up to that bin. So if you're in the first bin, obviously you only have one bin to count. So it's 7.4. Now in the second bin, anything up to that bin has a 40.7% chance of occurring. So anything from 45 to 59 has a 40.7% chance. Now, if you go to the third bin, there is a 65.4% chance that 45 to 66 inches of rainfall. Now, you just keep adding pretty much. You just accumulate. You accumulate each of the frequencies. So the first one you start with, obviously the first value. And for the second one, you see now you're adding this one plus this one. And for this one, now you're just adding the first 3. Then for this one, you're adding the first 4. And then for this one, you're adding the first 5. Or if you'd rather, to be able to just drag down the equation. Which one is it? This one. So if you wanted to just drag down the equation, you could just do the current bin plus the probability of all the previous bins. So the value above it. So what you're doing here, you see? So now we're adding this bin to the probability of the values. So this 20% represents 0 to 6. So what you're doing is just adding this bin to all the previous values. So this just accumulates here. So pretty much what you could do, you obviously set this first value. Then once you set up this second value where you add this new bin to the last bins, you could just drag down the equation. And then it should give me the same values. So if we go back to this, so this is the cumulative distribution. So for the histogram, you're just taking the frequencies here for each of the bins and then plotting it in a bar graph or a column graph. So you see, you're taking the bins, which are your labels, and the frequency. So if you want it, so you're gonna select the X values, press Control, and select the frequency. So now you can select 2 different areas at the same time. And then you go to insert a column graph, 2D column graph, this one. And then you add the axis titles, you add the title, and there you have it. So that's your histogram. Histogram is pretty much just plotting your frequencies. Now for the cumulative probability distribution function, you do the same thing here. You go select the X values. Oh, sorry, you don't select the X values. You could how should you do it here for you? So here's this graph here. Yeah, so you just, here she used, in the classwork, she just used the upper values. So that's what we're gonna do here. So we're gonna select the upper values, that's your X values, and then press Control, hold Control, and then select the cumulative distribution. Then you insert a scatter plot with smooth lines, and then you could remove the legend because there's only one graph here, and then add axis titles and your chart title, and this would be the number of product defects, like this one here, and this would be the cumulative distribution function. So for example, so anything, let's see, anything up to 9, as you can see here, anything up to 9 has a 55% chance of occurring. So as you add more, like if you increase the amount of product defects here, you see that there's a higher probability of this happening, of anything of 13 and below, 13 number of product defects and below of occurring. So at, let's see that at 12, there is an 85% chance that 12 or less product defects occur. And that's what the cumulative probability distribution function tells you pretty much. And I think that's it. If anyone has any other questions, you feel free just to ask in the chat.